All right, let's dive right in. We're going to talk about the universe's most extreme collisions. What actually happens when you take the ultimate cosmic vacuum cleaner, a black hole, and feed it the most powerful fuel source in existence?
I mean, think about it. What if those black holes, the titans of cosmic destruction, aren't the main event? What if they're just the stage for something way, way more violent? Something that unleashes a power we can barely even create here on Earth.
Because, well, that's the kind of power we're talking about. The energy that's blasting out from around supermassive black holes, it can literally outshine its entire galaxy. You've got a single point of light that is brighter than 1 trillion stars. So what in the universe could possibly do that?
To get that answer, you first have to meet the culprit. It's this incredibly elusive, mysterious stuff called antimatter, or as I like to call it, matter's evil twin. And look, this isn't science fiction. Antimatter is absolutely real. It was actually predicted by the physicist Paul Dirac before it was ever even discovered. The idea is pretty simple, actually. For every single particle of matter that makes up you and me and everything, there's a matching antiparticle. So an electron has a negative charge, right? Well, its antiparticle, the positron, has the exact same mass, but a positive charge. Same thing for protons and antiprotons. They're like perfect, spooky mirror images of each other. But here is where it gets wild. When these two opposites meet, they don't just bump into each other. No, they completely annihilate. They vanish. Poof, gone in a flash of pure energy. This isn't just a reaction. It is a 100% conversion of mass into raw power. And the amount of energy we're talking about is, well, it's staggering. If you took just 1 gram of antimatter and let it meet 1 gram of regular matter, you'd get an explosion equal to 43 kilotons of TNT. Let's just put that into perspective for a second. That is nearly 3 times the power of the atomic bomb that fell on Hiroshima. And all of that, from a combined mass, you could fit inside a single sugar cube. It's just an unbelievable amount of energy.
So where in the cosmos could you find enough of this stuff to light up a whole galaxy? Well, you have to go to one of the most violent places imaginable, right to the edge of a black hole. Let's take a look at how this cosmic engine actually works. See, around a black hole, you've got this swirling vortex of superheated gas and dust called an accretion disk. The material here is spiraling in at up to half the speed of light. The friction from that motion heats the disk to billions of degrees. That's hotter than our sun's core. And that inferno, it becomes a literal particle factory. In that insane heat, a process called pair production just kicks into overdrive. Basically, high-energy photons, particles of light, are flying around with so much energy that they can spontaneously split into 2 particles, one of matter, an electron, and one of antimatter, a positron. The light's energy literally becomes mass. So you see what's happening here. The black hole's accretion disk is constantly making its own fuel. It creates these matter-antimatter pairs from pure energy, and then they immediately find each other in that dense, chaotic disk and annihilate, releasing even more energy. It's this incredible, runaway, self-fueling engine. And just look at how efficient this engine is. Annihilation converts 100% of mass into energy. 100%. Now, compare that to nuclear fusion, the very process that powers our sun, which converts a measly 0.7%. This is it. This is why the area around black holes can be the most luminous thing in the entire universe. But all that incredible energy doesn't just hang around. Oh no, it has massive cosmic consequences. It acts as this incredible force that can both create and destroy on a galactic scale. A huge amount of this annihilation energy gets grabbed by intense magnetic fields and blasted out from the black hole's poles. We call these relativistic jets. These are streams of particles fired out at an absolutely unbelievable 99% of the speed of light. And these jets are just colossal. I mean, they can stretch for millions of light years, way beyond the galaxy itself. As they tear through space, they can slam into giant gas clouds and trigger a huge burst of new star formation. But they can also do the opposite. They can blow a galaxy's star-forming fuel clean out, shutting down its growth for good. And this isn't just a theory anymore. We're actually watching this happen. The James Webb Space Telescope has given us these amazing images that show these powerful outflows literally sculpting galaxies in the early universe. It confirms that this whole process has been a key part of how the cosmos evolves.
But, studying this cosmic engine, it does more than just tell us about galaxies. It pushes us right up to the edge of what we know, and it forces us to ask some of the deepest, most fundamental questions in all of physics. Which brings us to the big one. If the Big Bang created equal amounts of matter and antimatter, they should have just canceled each other out, right? Annihilated completely, leaving a universe with, well, nothing. So why is there anything? Why are we here? It's a puzzle called baryon asymmetry, and honestly, it's one of the biggest mysteries out there.
And scientists are tackling this from every possible angle. At CERN, they're smashing particles together, looking for any tiny difference in how matter and antimatter behave. Up on the International Space Station, an experiment is hunting for stray antimatter from space. And telescopes like Webb and Chandra are searching for that telltale 511 keV gamma ray signature of annihilation happening right now, hoping these cosmic engines hold the key.
Which kind of leaves us with this final incredible thought. Maybe black holes aren't just about destruction and creation. Maybe they're cosmic laboratories, running experiments at energies we could never hope to achieve. And maybe, just maybe, by studying these extreme collisions, we'll finally figure out why we live in a universe of matter, and in doing so, maybe we'll even learn the ultimate fate of the cosmos itself.